In this screencast, we're going to learn about calorimetry, specifically what it is, how does a calorimeter work, and how do calorimetry calculations work. So first off, what is calorimetry? It's the study of heat flow and heat measurement. You can see the STEM word calorie there in calorimetry, which implies this has something to do with heat already. And it's just studying how the heat flows from one object to another and how to measure that. Heat can be a slippery thing to measure because it's just it's warm energy that seems to pass from object to object. So it can be difficult to measure directly. However, the transfer of heat can be measured by changes in temperature. We can measure how warm or how cold something is when it contacts something else that's of a different temperature, and that's the basis of doing calorimetry and calorimetry measurements. Also, calorimetry calculations are possible due to the law of conservation of energy. Now, this is similar to the law of conservation of matter or mass that you've learned about already, except you substitute that word, matter or mass, with energy. And again, that states that in any chemical reaction, energy is neither created nor destroyed. Energy doesn't disappear into nothing, nor does it appear out of nowhere. We always have the ability to follow it and to be able to make sure that we can see where it goes from one form to another. Again, it doesn't just vanish into nothing. Specifically, when you're dealing with calorimetry in warm objects and cold objects, heat lost by one object is equal to heat gained by the other. Heat, again, doesn't just disappear into nothing. It typically gets transferred, and it always gets transferred in a one-way direction from a warmer object to a colder object. You'll never, for example, hold an ice cube and suddenly your hand will get all nice and toasty from holding that ice cube because, of course, your hand, presumably, is going to be warmer than the ice cube, so the heat energy from your hand is lost into the ice cube, which is colder. Now, this can be calculated out using an equation Q equals mc delta T, which you're already familiar with. Q, again, is heat energy. M is the mass of the object that you're analyzing. C is a specific heat constant specific to that object. It's a measure, again, of how quickly or how slowly something can gain or lose heat. And change in temperature is just that. It's the final temperature minus the initial temperature. Now, we can take the law of conservation of energy and we can combine it with the Q equals mc delta T expression to come up with this new one. Negative Q equals positive Q. Now, mathematically, that doesn't make a lot of sense because if you plug in a number for Q, make it 4, let's say, negative 4 equals positive 4, it certainly doesn't make a lot of sense mathematically. However, if you look at it from the perspective of calorimetry, and if you look at the signs a bit differently, it does make sense. Because what we're doing here is that sign right there, this negative sign, whoops, there it is, and this positive sign indicates direction. Pardon me here while my penmanship gets better. Direction. It indicates which way the heat is flowing. So for example, if you have 100 calories lost by one object, that must mean that those 100 calories are gained by another object. Again, the heat doesn't get lost and just disappear into nothingness. That heat is transferred from one object to another. So we're talking about the same 100 calories, and the negative sign right here indicates a loss of heat energy, versus the positive sign, which indicates a gain in energy. So it's, again, that same 100 calories of heat energy that are conserved, they're just being moved from one object to another. Now, calorimetry can be measured using what's called, in this case, a coffee cup calorimeter. And as the note says here, calorimetry experiments determine the heat changes of reactions by making accurate measurements of temperature changes in a calorimeter. Heat can get lost very easily to just about anything that's of a different temperature, including the air around it, around an object. So we have this coffee cup calorimeter. Coffee cups made out of styrofoam are pretty good insulators. Heat is seldom lost through them, which is why they make great containers. So in this case, we have, it looks like 2 coffee cups nestled into one another. We have the styrofoam cover right up top to avoid any heat loss to the atmosphere. And then we have a stirrer because we have to be able to mix whatever is in here. In this case, it's water, and the thermometer. The idea is that some sort of metal is going to be added to this water solution right here. And presumably the metal is going to be, we'll just call it hot. It's going to be somewhat hot. It should be warmer than the water that's in here. Now we can take that metal, we can drop it into this coffee cup calorimeter, and we can do it as quickly as possible. Just open the lid, open the cover, drop the metal in, close the lid. Metal is going to sink to the bottom, of course. The stirrer will then do its job. It'll stir, so someone will grab the end right here, and that'll stir it up and down. And that's because, of course, there's a density change, so the warm water tends to separate out from the cold water. So we need to keep stirring it so that the water is a uniform temperature. And then whoever drops the metal in there can then measure the change in temperature using the thermometer and do some interesting calculations. You can identify, for example, The mass of the metal, if you didn't know ahead of time. We could identify the specific heat constant of the metal, which helps us identify what the metal is, because every metal has its own unique specific heat constant. We can also determine the change in temperature, because the metal will get a little bit colder, the water is going to get a little bit warmer, they're going to reach what's called thermal equilibrium, which means the temperatures of the two are the same, eventually, if you let it sit there long enough. And based on how high the temperature of the water goes, we can calculate out what the initial temperature of the metal must have been, which is very difficult to determine otherwise. You can't just stick a thermometer into a hunk of metal and then figure out how warm that metal is. Instead, we can do this indirect calculation and get very accurate results. So here's what these calculations and these problems look like. Here's an example. And if you can't have out a paper and pencil, again, have out a paper and pencil so that you can do these calculations in your notebook. You can show these to your teacher tomorrow and you can follow along with what's going on. We have a 97-gram sample of gold at 785 degrees Celsius dropped into 323 grams of water, which has an initial temperature of 15 degrees Celsius. If the gold has a specific heat of 0.129 joules over gram times degree Celsius, what is the final temperature of the mixture? One thing that I'll note here too is that it's going to be in water. Water has a specific heat constant that you should be somewhat familiar with. It's 4.184 joules over gram times degree Celsius. And we'll be using that a lot in calculations. So here we go. Here's the same problem with a little bit of animation that's coming up in just a moment. What I would suggest that you do, what I urge all my students to always do, is to create a little table where you've got the metal and you've got the water. And you can kind of sort through all the information in a problem and put it all together. And let me label this as metal, because we're going to have a mass. We're going to have a specific heat constant. We'll have an initial temperature. And we'll have a final temperature. And there's a lot of data in this problem, so it's good to kind of just fill in this little table so you can keep track of everything and not mix something up. For example, you don't want to have the specific heat constant of the water with your metal calculations. So I'm just going to go ahead and fill in numbers. 97 grams. This constant is 0.129 joules over gram times degree Celsius. The initial temperature is a whopping 785. Final temperature, we don't know. Water. The mass of the water is 323 grams. Its constant, again, it's not written here, but I mentioned it in the previous slide, 4.184 joules over gram times degree Celsius. The initial temperature of the water is 15 degrees, and the final temperature, we have no idea. One thing I want to mention about these temperatures, because, and we'll see an animation here in a moment, is when the metal drops into the water, you then have this combo. Your new system is this metal-water combo. And the final temperature should be the same for the metal and the water. Now, again, why is that? That's because the metal is immersed in water, and if you let it sit there long enough, they're going to both reach the same temperature, and then you'll have, in essence, a stoppage of heat flow. They call it thermal equilibrium, which means that both objects are at the same temperature, ultimately. So when we do our calculations, and this will make sense, a little bit more sense in just a moment, the final temperatures of the metal and the water should be the same because the metal is submerged in that water. So there's a piece of gold off here on the side. Here's some fancy animation. Excuse me. There's a beaker of water, 323 grams, 15 degrees Celsius. Now, the idea, again, is that the metal is going to lose heat and the water is going to gain heat. So this goes back to the negative Q equals positive Q expression that was present a few slides ago. So the substance that's losing heat, I'm going to do all the calculations regarding that on one side, and the substance gaining heat is going to be on the other. Now, what's gaining heat? Well, the water is going to be gaining the heat. It's only at 15 degrees, and you have a hunk of metal dropped into it that's at a really high temperature, at 785 degrees. So what's going to lose heat? The metal is going to lose heat. So the calculation here is nothing more than a fancy mc delta T equals mc delta T calculation with a negative sign inserted into that. And that has to be thrown in there for the calculations to work. Let me show you. So there's kind of a rewrite of mc delta T, mc delta T. C you mentioned, or C you probably saw this in the previous screencast, can sometimes be written as Cp. So here's the specific heat constant of the gold, the mass delta T, specific heat constant of water, the mass delta T. Notice the negative sign right here at the very beginning. That's crucial. You have to go in and you have to artificially add that. If you don't have that in there, your calculations will not work out properly. Plug in numbers. The units are also plugged in there as well so that you can see what they are. We can go ahead and clean it up a little bit, drop the units because they're the same on both sides. Notice how the temperature is written out. Final minus initial, we're looking for the final temperature for both things. The TF is going to be the same. And then as you proceed through, this just becomes a sophisticated algebra problem. Notice that negative sign right now is distributed. The 12.5 multiplies through TF minus 785, and the negative sign is attached in there as well. So the negative sign becomes incorporated into this. The 12.5 minus 785 should have been a negative number, but because that negative sign is distributed, it instead turns into a positive number. Again, you need that for this calculation to work, otherwise you'll end up with really kind of wonky numbers. And as you do the math, the final temperature ought to work out to be 22.1 degrees. So it might be in your best interest to do the math on your own and plug the numbers in through the calculator to make sure that this does work out the same way as for me as it does for you. Another example, same type of problem but solving for a different variable this time. 240 grams of water initially at 20 degrees Celsius are mixed with an unknown mass of iron initially at 500 degrees Celsius. When thermal equilibrium is reached, the system has a temperature of 42 degrees. Given the specific heat of iron, 0.4495 joules over gram degree Celsius, find the mass of iron. And again, it's not written here, but the specific heat constant of the water, 4.184 joules over gram degree Celsius. Okay, now I'm going to pause for just a second. I'm going to go ahead and actually write in my little table, my metal table and my water table, get all my data straight, realize what I'm solving for. And if you can, try to do this on your own. You know everything that you need to be able to solve this. So try this on your own after you create your little data table. See what you get for the mass of the iron. I'll go through the next slide really quick and we'll see what you do. Okay, here's the next slide with that problem rewritten in my little table right there. You'll notice that the final temperatures are equal. The 42 degrees are equal for both. My initial temperature, 500 degrees for the metal, 20 degrees for the water. Constants, 0.4495 is my specific heat constant for the metal, 4.184 is for water. The mass of water is 240 grams. The mass of my metal is an unknown. That's my variable. All right, there's the fancy animation. We don't know the mass. Again, Q lost equals Q gain for this problem. So negative Q equals positive Q. Again, the negative sign has to artificially be added in. Hopefully you did that if you did the problem already. Here's what the calculations ought to look like, or at least the initial setup. Everything's plugged in except for the mass right there of the metal because we don't know what that is. You'll notice on the far right side of the problem, those are all numbers, so we can calculate all of that in just a moment. So this algebraic problem becomes a little bit easier because you're going to end up with a number times x on the left equals some number on the right. Drop units, you get this little simplification. And here you go, 205.9x equals 22,091. Divide both sides, get x by itself. You should be getting a mass of 107.3 grams of iron. If you got that or something in the ballpark of that, then you're certainly on pace. This problem doesn't pay any attention to significant figures, although it ought to. And it was written a little bit sloppily in that the temperature only has one sig fig and the water only has two. But if you're getting this same ballpark answer, 107.3, then you're doing this right. There's one last problem to do. A 5-gram piece of metal heated to 50 degrees Celsius is dropped into a beaker of water, 100 grams of water specifically. That's initially at 20 degrees Celsius. After a few minutes, the temperature of the systems level off at 35 degrees. What's the specific heat of the metal? Just to give you a preview, we'll be doing an activity that relates to this exact homework problem in the future, so you should be able to do this. Please do this on your own and have this ready so that you can discuss this with your teachers when you come to class the following day.